EI. This one we put into here minus omega 24x4 plus 12 omega L x3 plus bx minus 24 omega L. Again, one more mistake. This one should be 2. Right? Because here I multiply BL here. So here should be 2 and x. That's it. And let me compare my solution. So this is a diffraction of the beam. So that means the beam will be deformed in some kind of shape, and this shape will be described by this function here. Okay, so here this is the y.
Wait, why isn't it? Hold on, I have a
The sign convention is this. You can see this is our corner system here. And for this case, this is our diffraction. So here for sign convention, for diffraction is downward positive. Yes.
I still don't understand why it's 2.
Huh?
Shouldn't it be 3 because...
Oh, yes. Sorry. Let me change back.
3, yeah, so.
That should be 3. So this should be 3. Yes. Okay, so that would be the dimension to the force. Dimension, yes, that would be 3. Sorry. Anyhow, the sign convention here is not that, well, it's not that critical. As long as you can see, this one, the beam has been pressed down. So basically, we expect the diffraction will be going down. And this equation tells us is the magnitude. Okay, so for example here, and we can calculate the maximum will be at the middle here. So at the maximum, we can simply calculate is introduce x equal to half of the L. So from this equation, basically that's why you can easily use program to draw the curve or to calculate the diffraction at any point. Any questions? So this is a very detailed calculation process for, we can try 10 minutes. We can try the other example.
Wait, let's solve for your y then?
Huh?
So we're solving for y then, but then how does that help us? Like, how do we confused on like y?
Yes, we have a formulation for y, and that is the diffraction.
So that's just the deflection.
So diffraction, that tells you how vertically the beam is deformed by the loading. And sometimes for certain design, the people might want is, okay, for this design, the maximum diffraction here shouldn't exceed certain amount.
And then that's where you plug in your x as your distance.
Yes.
Okay, so
Yeah.
you have a formula for it. Okay.
Yes. So for this case, we see the different one. So this is simply supported. But for this case, we have the loading, point loading, and the distance is L over 4 and 3L over 4. Okay. So now again, we want to calculate y of x. So starting from, we have to know is EI. We utilize the equation EI double prime equal to m over x. So by all means, we have to know the distribution of the m first. So you can try anyways. Anyways, I prefer is go to use the bending curve because that would be easier. So this is the m, this is a v. If I use the same approach, and let me do this one quickly. So this one will be equal to, this is p over 4. This is 3p over 4. So the diffraction will be equal to this. then the bending will be this. So for this one, the bending moment m of x will be equal to, we do this carefully, the magnitude will be 3p over 4x. Okay, so this is the 16, 3 PL, this value here. Okay. And for this one, the m of x will be equal to minus px4 plus 4 PL. So you see, for this example, how many distinct functions for m? We have 2. Right. So right now here in our calculation, we have to split our integration into 2 ranges. Okay. So for this one is ei y double prime equal to p3 4x. For this one is ei double prime equal to minus px 4 plus pl over 4. So individually we integrate the things. So for this one, the calculation rigor will be double of what we have done here, right? So because for different range, and so this one, this range is between x and L over 4. And for this range, that is between L over 4 less than x less than L. From here, that kind of give you a thinking is for complicated loading of the beam, we might have more than 1, 2, 3, 4, or etc. different ranges. And then you have to simply do the calculation range by range. Okay. Let's proceed to see. Okay. So for this one, this will be, say, ei y prime will be equal to, here, because this is the second integration exercise, so I won't write down so detailed. I just write down directly. So here is 3p 4 times 2x squared plus the first integration constant. Let me call it a1. So ei y will be equal to 4 3p and 6x cubed plus ax a1 plus b1. Are we okay? Okay, so that should be very easy. And then for this one, that is ei prime equal to minus ap x squared plus 4plx plus a2. And ei y will be equal to minus 24p x cubed plus a. So right now we have integration constant a1, b1, a2, b2. How many unknowns? 4. 4 unknowns. And how many boundary conditions we have? 2. 2 boundary conditions with 4 unknowns. How could we solve for this problem? See, that is come to the point here. For this problem, that is valid in this range. So by all means, the boundary conditions we're looking for here, listen, this is a key. To solve for the boundary condition A1, B1, to solve for this A1, B1, we have to look for the boundary conditions that is falling into this range. If you will try to look for the boundary condition outside this range, it's not valid, right? Because this equation only valid in this range. So here we have the boundary conditions is here. The first one here, so that is at x equal to 0, we know the y equal to 0. How about for the second one? Loading? Okay. So we're looking for at the position of the loading here. Okay. So that means we're looking for, say, let me say this is the diffraction. Let me draw the diffraction here. I don't know diffraction, I just aptly draw it. So here at the position of the loading. So this is the diffraction here. And this is the slope here. So the second boundary condition is this, at the place of the loading, which means at x equal to L over 4, diffraction should be equal to, say, let me call this is, say, y, I don't know the value, say, let me call this is a y star. Okay, and for this case, let me write it up here. For this case, the boundary conditions is, again, we have x equal to L, y equal to 0, and x equal to the loadings, then diffractions will be equal to y star. And let me use the color here. Right? So combine the both equations. Here is come to here. Let me call this is, to make this distinguish, let me call this is a y1, okay? So let me call this is a y2. So that means y1 at L over 4 equal to y2 at L over 4. So this is the equation boundary condition 1, this is a boundary condition 2, so this will be boundary condition 3. And one more, because we have 4 unknowns, right? We have 4 unknowns, A1, B1, A2, B2. So 4 unknowns, we must have 4 conditions. What will be the last one? Slope. Huh? The last one is the slope here. You can see the curve, they meet at here, the slope at y1 must be equal to the slope at y2. So that means y1 from L over 4 equal to y2 prime. Sorry, it's too low, but this is equation 4. Are we okay? So coming back on Friday, and let us finish this one. So that is the 4th condition, and I will